Hello everybody, and this is a video for the Coopersmith Career Consulting Introduction to Statistics MAT 102 course. What I'm going to do in this video is I am going to look over the practice exam that appears in the Coopersmith materials. Hopefully you have access to it. What I would highly suggest is that after you study the materials, or listen to the original crash course, you try to do the statistics practice exam on your own. And then when you finish it, there is an answer key at the end of this syllabus. Obviously, you don't want to look at the answer key before you do it. That would kind of defeat the purpose. But what I'm going to do in this video is I'm going to go through the answer key with you and kind of describe all of the answers to help you not only know the answers, but also know how the answers were derived. So let's first find the practice exam. This is the syllabus, of course. You have the course objectives, the textbook, all sorts of information. And then at the bottom of the syllabus, after you have all the readings, you then have the practice exam over here. So what I'm going to do is there are 50 questions altogether. Please do yourself a favor, do the exam first before you watch this video. If you haven't done the exam yet, please turn off the video. It will still be here when you get back, I promise you. And we're going to go through these questions one at a time. So let's start with question number 1. Identify whether this statement describes inferential statistics or descriptive statistics. The chances of winning the California lottery are 1 chance in 22 million. Now, the difference between inferential statistics and descriptive statistics is that inferential statistics regard drawing conclusions from data that are subject to variation or subject to randomness. For example, the chances of winning a raffle, or the chances of it raining on a particular day of the year. Something that you are inferring from or is subject to some sort of randomization. Descriptive statistics, on the other hand, are statistics that merely recite the collection of information. A quantitative description. A descriptive statistic would be 100,000 people played the lottery last week. But something like the chances of winning the California lottery are 1 chance in 22 million, that is inferential. And so therefore the correct answer for question number 1 is A. Let's take a look at question number 2. Determine whether the data is qualitative or quantitative. Well, quantitative data means data that is based on a number. There are 10 people in the room. It is 75 degrees outside. Something that just is a statistic based on a number is a quantitative statistic, whereas a qualitative is not something based on a number, something that tells you the color or the quality of something. The colors of the automobiles on a used car lot are, of course, qualitative and not quantitative. A quantitative example would be there are 50 cars on the lot. Question number 3 asks you to identify a particular set's level of measurement. Now I'm going to show you a website over here that gives you the distinction between these types of statistics and what they mean. A nominal statistic refers to categorically discrete data. Something that simply establishes what the name of something is, or that identifies a characteristic of it. Doesn't really have to do with a particular number. Ordinal refers to quantities that have natural orderings. A ranking is an ordinal statistic. A rating scale of 1 to 10 is an ordinal statistic, something that implies an order to something. Interval statistic, the third one, that makes up the third of the 4 choices, is kind of like an ordinal statistic, except that there are regular intervals between each value. And again, an example, temperature. 80 degrees and 60 degrees, of course, are both statistics. You can say one is hotter and one is colder. That would be an ordinal statistic would be the 80-degree day is hotter than the 60-degree day. If we had 3 days, 50 degrees, 60 degrees, and 80 degrees, the ordinal would say the first day was the coldest, the second day was the second to coldest, and the third day was the hottest. The interval statistic, on the other hand, is something that's a little bit more specific, that shows you the levels between the numbers that we're referring to. 60 degrees as opposed to 80 degrees are 20 degrees apart. That is an interval. And finally, you have ratio, which has a natural 0 point, similar to interval, except that time, or number of degrees on a scale that starts at 0. Anything that starts at 0, 1 minute, is an interval data, but that starts at a 0 point. Not a contradiction from interval data. In fact, ordinal, interval, and ratio are all really the same kinds of data, but they have different characteristics. Ordinal is any list, any ranking. Interval is something that has any particular benchmarks that you're measuring. And ratio is also interval, except that it starts at a natural 0 point. So getting back to our example, number 3, identify the level of measurement, hair color on a women's high school tennis team. Now here there are no numbers being established at all. So it's not ordinal, nominal, or ratio. So not ordinal, interval, or ratio. The only one that makes sense is nominal, because nominal is just a description, like a name. A color is like a name. It doesn't depend on any particular number. Okay, let's look at 4 and 5. We've got decide which method of data collection you would use to collect the data for your study. Let's discuss the definition of all of these. Simulation is when you use something like a computer to simulate what the results of something would be. For example, if you want to know if you flipped a coin 1,000 times, what would the odds be of what would you get in terms of heads and tails, you could run a computer simulation to pretend it's done 1,000 times and tell you what the results would be. An experiment, of course, is when you test a particular characteristic of something and see how often it works out. A survey is when you simply gather data, just ask people or look at a chart and determine what a particular set of numbers are. The most common thing you have in terms of surveys is when political surveys. They call you up and say, which candidate are you voting for? An observational study is when you're simply watching something and seeing what will happen. So we've got 2 examples of this. A study where a drug was given to 23 patients and a placebo, which means a drug, it's something that looks like the drug but isn't actually the drug, to another 23. And we want to determine if the drug has an experiment. This, of course, is a classic description of what an experiment is. You give half the people the drug and half the people you don't give the drug, see which one heals, see which one doesn't heal, and make a determination of whether the drug works. That is a classic experiment. So we're going to choose B for that. A study of salaries of college professors in a particular state. Well, you don't really need to experiment that. You don't really need to simulate that. All you need to do is survey it. You need to ask the colleges, whether it be in writing or in orally, whatever it is, what the salaries are. So for that one, all you'd really need to do is a survey. Number 6, also a very easy question. Use the frequency distribution, this thing over here, to find the class width, class midpoints of the first class, which is this one, and the class boundaries of the first class. Class width simply means how broad the class is, each class is. Well, you can see over here that each class width seems to be 5 pounds. 135 to 139 is 5, 140 to 144 is 5, 145 to 149 is 5, etc. In other words, each class has a width of 5 pounds from one end of the class to the other end of the class. So that would be 5. Class midpoints of the first class, well, that's easy. The first class is 135 to 139. What's in the middle? Well, the answer, of course, is 137. You got 135, 136, 137, 138, and 139. The value in the middle is 137. You can also take the average of 135 to 139, add the 2 things up, and divide by 2. You're going to get 137 either way. And the class boundaries of the first class, which asks you what data point is the lowest that can get you in class 1 and what data point is the highest that can get you in class 1. Now it sure seems like it's between 135 and 139, right? It's actually a little bit broader than that because you can see these are all rounded off to the whole numbers. So if something is at 134 and a half, it'll still be rounded up to 135. And if something is at 139 and a half, or almost a half, it'll still be rounded up to 139. So the actual class boundary is between 134.5 and 139.5. Actually, slightly less than 139.5, because if it was 139.5, it would actually be rounded up to 140 and be in this next class. But still, the class boundaries, you can still pretty much say that it's between 134.5 and 139.5. I guess it would be more accurate to say between 134.5 and 139 and 0.4999999, but you can still basically just say 139.5. Okay, number 7. Use the chart to approximate the number in this sample. Now, the key to this one, of course, is that this axis is the number of hours of leisure time that the students have, presumably per week. And now this side is a cumulative frequency. Cumulative frequency means how many the numbers build up from one to another. So, for example, what this chart means, when you have at 9.5 hours, you have almost nobody. At 14.5 hours, you have 10 people. At 19.5 hours, you have about almost 40 people, but that means that's the total number of students who have up to 19.5 hours. And then when you get to 70, it's up to 24.5 hours. To the point where when you have 39.5 hours, the cumulative frequency, which means all of the college students in the sample, have approximately 39.5 hours or less of leisure. So the total number of students in the study is approximately this, approximately 80, because cumulative frequency means the total number up to that point, the total number that have up to 39.5. So this would be approximately the top of the chart, which comes out to about 80 students. That's what I would estimate. I think if you put 82 or 83, you could probably make an argument for that also, something like that, but it's approximately 80. Okay, let's take a look at number 8. A student receives test scores of 62, 83, and 91. The final exam score is 88, and the homework score is 76. Each test is worth 20%, the final exam 25, and the homework score of 15. What is the student's mean score for the class? Mean is the average, and you have to weight each thing by what the problem tells you to. So what I'm going to do is over here, I'll take this over here, and we'll take the 3 scores. We have 60, which counts at 20%. Okay, we've got an 83, which also counts for 20%. Then we've got 91, which counts also for 20%. Those are the 3 exam scores. Then we have the final exam score, which was 88. That counts for 25%. And then you have the last one, which is 76, and that counts for 15%. So if we multiply each of these, if they were all equal, you could just add them up and divide by 5 to get the mean. If they were all 20%, if they were all equal. Here you simply have to multiply each one by the percentage and just add them up at the end. How do you do that? Well, 60 times 20%, 1/5 of 60 is 12. 1/5 of 83 is 16.6. By the way, if you can't figure this out in your head, you can simply do it on a calculator. Let me open up a calculator, as a matter of fact. Here's the calculator. Okay, 91 times 0.20, so we'll do 91 times 0.2, which is 20%, which gives you 18.2. Let's see, 18.2. I'm doing this relatively slowly, but okay. A quarter, 25% of 88, that's obviously 22, because a quarter of 8 is 2. And 15% of 76, let's do this on the calculator as well. That is 0.15. 0.15 times 76, and you get 11.4. Okay, let's add these all up together, which comes out to a total of 80.2. If you added them together, you would get a total of 80.2. So the entire mean for the student is this amount. They're each weighted. Again, it would be really easy if they were all equal, just add them all up, divide by 5. Here you have to do a little bit of a weighting by multiplying each by their percentage. 0.2 is 20%, 0.15 is 15%, and 0.25 is 25%. Next, we have number 9. Number 9 is the mode. Remember, mean means the regular average. Add them all up and divide by that number. Median means the middle one, the middle score. And the mode means the one that happens the most often. Now, if we look at the top 10 finishers at a golf tournament, find the mode score. Well, let's see. We've got 2 incidents of 67. It looks like we've got 4 incidents of 72. We've got 168, 173, 171, so clearly 72 is the mode. If you wanted the median, you'd line them all up in order and pick the middle one. If you wanted the mean, you'd add them all up and divide by 10. If you want the mode, just see which one occurs the most often, and clearly 72 is the one that occurs the most often. Okay, the cost of 5 homes in a certain area is given: 173,000, 181,000. 201,000, 171,000, and 1,251,000. Next question is, okay, fine. So mid-range. Now, mid-range means the average of the two extremes. You take the smallest and the largest, add them together, and you will have the mid-range. So in our case, let us take the smallest value, which is 171,000. And the largest value, which is 1.251 million, 1,250,000. And let's take the average of those two. Let's again, we can use our calculator. We don't really need to use our calculator, but we will. Why not? 171,000 plus 1,251 million, and divide that by 2, and you have your answer, which is 711,000. Again, mid-range, extremely easy. Take the whole range, which is the difference between the largest and the smallest value, and divide by 2. Get the average of those two. All right, a coin is tossed. This is an easy one. Find the probability that the result is heads. Well, the way you figure out the probability of anything is the number of chances that you're looking for divided by the total number of possible chances. Now, when you're tossing a coin, you only have 2 chances, 2 possibilities, heads and tails. And what you're looking for is heads, which is 1 out of those 2. So the answer is 1 out of 2, or 0.5. Okay, a six-sided die is rolled. Find the probability of rolling a 7. Well, a 6-sided die only has 6 sides. So the probability of rolling a 7, there are 6 possible chances, but none of them are a 7. So the answer is 0 out of 7. If they wanted to know what are the chances of rolling a 1, it would be 1 out of 6. If they wanted to know what were the chances of rolling a 2, it would be also 1 out of 6. If they wanted to know what were the chances of rolling, let's say, an even number, well, there would be 3 even numbers, 2, 4, and 6, so it would be 3 out of 6, or 1 out of 2, whereas the odds of rolling a 7, of course, are 0. Let's look at number 13 over here. Now, number 13 says, classify the statement as an example of a classical probability, empirical probability, or subjective probability. So obviously, first thing we got to do is define those things. Well, classical means probability when all the events are equally likely. Probability of rolling or flipping a coin and rolling 3 straight, or flipping 3 straight heads, something like that. Classical probability just means, in general, the probability of certain things happening, assuming that all the probabilities are equal. Empirical probability means the ratio of something that may happen to all the different possibilities. And subjective probability is something where you're using your own personal judgment to determine the probability of something happening. So if I say the probability that a train will be in an accident is 1%, well, that looks like an empirical probability. It's not classical probability because obviously the 2 events, yes accident and no accident, are not equally likely under these facts. It is an empirical probability because it's a ratio of what we're looking for, in other words, an accident, with regard to the total chances, which are 100% altogether. And it's not subjective because it's not relying on anybody's personal view or personal subjective opinion. Okay, question number 14 over here. You are dealt 2 cards successively without replacement from a standard deck of 52. Find the probability that the first card is a 2 and the second card is a 10. Round your answer to 3 decimal places. Okay, well, let's see. When you do when you do two different events and the probability of both of them happening, you have to multiply the two possibilities. You have to figure out what the odds of each one are, and then you got to multiply them in order to figure out what the answer is. If it's or, if they ask you what's the probability of this happening or that happening, then you add the two probabilities together. But let's see. Okay, so the first card is a 2. Now there are 52 cards in a deck, and there are 4 2s in them. So the odds of picking a 2 are 4 out of 52. Okay, that's the first chance. What's the second chance? The second chance is how many cards are there left? Well, there are 51 cards left. How many 10s are there the second time? There's still 4 10s. You didn't pick a 10 the first time. So what are the odds of the second time? You got 4 chances out of only 51 cards left. So the probability of these two events happening is the top multiplied by the bottom. Now the 4 times 4 is 16, and 51 times 52 equals 2652. So it's 16 divided by 2652. And if you divide this, it asks you to round this to get a decimal. So if you divide this, according to my calculator, you get 0.00603318, etc., etc. But they ask you to 3 places, so these are our 3 places. Now the 6 we're going to round down because the next number is a 0, so our final answer is going to be this. Our final answer in terms of the probability of both of these things happening are 0.006, or about 0.6%. Next question. The access code to a house security system consists of 8 digits. How many different codes are available if each digit can be repeated? So 8 consecutive, well, that's a pretty easy one, right? Because each consecutive digit, there are 8 times in a row. How many digits are there? Well, it's 10 times 8. Because each time, there's 1 out of 10 chance. Each time you can pick a different digit. So it's 10 times 8, because there are 8 digits. There are 8 digits in the number, and there are 10 possible digits for each one. For each digit, there are 10 different possibilities. So it's 8 to the 10th power, which is a 1 followed by 8 zeros, and a 1 followed by 8 zeros is 100 million. So the answer that, as far as I can see, is 100,000. There we go. One followed by 8 zeros. Or you can, and that, which is 100 million. If you had a calculator, you wanted to do it, you would do 10 to the 8th power, or 10 times 10 times 10 times 10 times 10 times 10 times 10, etc. Okay, that is number 15. Just again, because you have 8 digits, and again, for each digit, there's a 1 in 10 chance of any particular digit happening. 7 guests are invited for dinner. How many ways can they be seated at the dinner table? If the table is straight with seats on only one side. Now for combinations or different possibilities, I mean, there are 3 different things that are covered. First of all, the first thing is if you want just what the different combinations are of any combination of things happening, like the order of 7 people in this case, the way you would do this is you would take the number of total people there are, and the total seats there are, which is 7, and you'd have to do 7 factorial. 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. Basically, it's 7 times, factorial means that number times everything beneath it. Now, if you were only picking 3 of the people, then you'd only have to do it 7 times 6 times 5. Then it would be something called 7C3. But we don't have to worry about that for this question, because this question they're just asking for the total different numbers of combinations. Now notice the difference between here and question number 15, because in question number 15, each digit could appear more than once. If in question number 15, digits could not be repeated, in other words, if the first digit was 3, you could never see a 3 again. If the next digit was 2, you could never see a 2 again. Then you would, instead of doing 10 times 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 10, whatever, 8 times, you would have to do 10 factorial. You would have to do, 10C8, because there are 8 digits. Then you'd have to do 10 times 9 times 8 times 7 times 6 times 5 until you have 8 numbers. So that's really the same question as number 16. It's 7 factorial. There are 7 people, and all 7 have to be seated. So it's 7 factorial, which is the same thing as 7p10, not 7c10, but don't worry about that for the time being. It doesn't matter in this particular question. So it's 7 times 6 times 5 times 4 times 3. Well, let's see. 7 times 6 is 42, times 5 is 210, times 2 is 840, times 3 is 2520, times 2 is 5040, I believe. I'm gonna pause it and check my own math. Yeah, that's right. Okay. So it's 5040 is the total number of possibilities. And now the logic behind that is the first seed, any of the 7 can be seeded. Now in the second seed, there's only 6 possibilities because one of them is already seeded. And the third seed, there's only 5 possibilities because 2 of them are already seeded. Then 4, then 3, then 2, and finally when you get to the last person, there's only 1 possibility because there's only 1 person left. So your total different number of combinations is 5,040. 100 people were asked, do you favor the death penalty? Of the 33 that answered yes, 14 were male. Of the 16 that answered no, 6 were male. If one person were selected at random, what is the probability that this person answered yes or was a male? Okay, well let's see. The first person. I'm sorry, there is only one person here. So let's see, how many people are there? 33 that answered yes to the question, 14 were male, so there were 100 people altogether. Let's say 100 people. And let's just put the numbers over here. 33 said yes. 67 said no. Of the 33 that said yes, they said 14 were male, which obviously means that 33 minus 14, which is 19 people, 19 people were female. Of the 67 that said no, 6 were male. Well, okay. And how many were female? So I guess there must have been 61 that were female. So we have an OR question here. So for OR, we need to figure out the number of people that are either answered yes or a male. Okay, so the people that answered yes was 33. Now other people that could also qualify are these 6 male people. So you have the 33 that answered yes, plus you have the 6 male people that answered no. Those are all the people that would qualify for this group. And so 33 plus 6 is 39. So you got 30. In other words, you have 39 total people that would qualify for either they're male, or they said yes. 6 are male that said no, and 33 said yes, so that's 39 altogether. Now there are a total of 100, so your answer would be, the probability would be 39 over 100. Or if you're putting in decimal points, it would be 0.39. Number 18. The random variable x represents the number of boys in a family of 3 children. Assuming the boys and girls are equally likely, find the mean and standard deviation for the random variable x. Now, in the crash course and in the slides, I covered standard deviation for distributions that were not binomial. In other words, distributions that had a lot more complexity. For standard deviations for those kinds of distributions, it was a little bit more complex. I didn't even cover for binomial distributions, so I'll cover it now. For binomial distributions, the formula for determining the standard deviation of a binomial distribution, simply take the square root of the n, which is the number of possibilities. Let me write that over here. N is the oops, sorry. All right. Anyway, n is the number of possibilities. I'll just put that over there. Okay, p is the probability of each. Of each of the possibilities. Times the 1 minus the probability of each one. In other words, it's a little simpler because it's binomial. There's only 2 possibilities. So in this case, The probability is the square root of n. There are three possibilities over here because there were three children. The number of events. Maybe I shouldn't have said possibilities before. The number of events times p, the probability of each one, which is 0.5, times 1 minus p. Now 1 minus p is 1 minus 0.5, which is also 0.5. 3 times 0.5 times 0.5. Now 3 times, the half of 3 is 1.5, times the half again is 0.75. And so the square root of 0.75, and this we can use a calculator for. Let me bring one up over here for you. Okay, so we have 0.75, and we'll take the square root of that, which comes out to approximately 0.87. So it's 0.86, etc., 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 but you can round it off to 0.87. So that would be our answer. Again, just apply this formula. N, which is the number of events that you're talking about, p times the probability of each one happening. Remember, it's a binomial probability, so it's either yes or no. You're not going to have different factors. You're not going to have different probabilities, times 1 minus the probability. It doesn't always have to be 50-50. In our case, for a boy and girl, it's 50-50. It could be something that's a 10% chance, in which you would apply 10 times 0.9, whatever the case may be. So one more thing before we go on to the next question. On the previous question, number 17, it also asked you, question 18, it also asked you for the mean. The mean means the average. Now, if boys and girls have an even chance of being born, and there are 3 children, the mean is, of course, just the average. And the average, of course, is going to be 1.5. It's 1/2 of 3. You could also figure that out by adding the possibilities. The possibility of each child is 0.5 being a boy, so that times 3 is 1.5. The next question, number 19, find the variance of the binomial distribution for which n is 800 and p is 0.88. Now the variance is this formula, except that you don't have to take, the standard deviation is if you take the square root. The variance is just what is inside of the square root. So the variance would be the n, which we said was 800 in the question, times the probability, which is 0.88, and times 1 minus the probability, and 1 minus the probability is 1 minus 0.88, so that's 0.12. So it would be 800 times 0.88 times, 0.22. And if we do that on a calculator, we get 84.48. So I'm going to write that as our answer, 84.48. That's the variance. If you want to take the square root of that, which would be something like a little bit over 9, that would be the standard deviation. Next question, question number 20. Now this is a very hard question. This is one that's, it's harder than any of the questions you're going to get on the actual final, I believe. And it's the sort of thing that we didn't really cover so much in the practice, in the crash course, but we'll cover it over here just to give you an idea of how to do this. So the question is, according to government data, probability that a woman between ages of 25 and 29 was never married is 0.4. In a random survey of 10 women of this age group, what is the probability that 2 or fewer were never married? Okay. First thing we need to realize is that there are 2 probabilities over here. I'll use never married, and the probability of never married is 0.4. That's 40%, and the probability of M for married we'll use as 0.6. Now they ask you what is the probability that 2 or fewer were never married. So there's really 3 possibilities here, and we got to figure them out one at a time. We got to figure out the possibility that 0 of them were never married, the possibility that 1 of them were never married. This is our little column for never married, and the possibility that 2 of them. And then we got to get the 3 probabilities, and then we'll add them up. Now, for each one, to figure out the probabilities, what you need to do is you need to take 10 use the C function. C is the combinations. Whenever you're using combinations of something, you figure out the extent to which the combination is necessary. For example, if you're looking at the possibility of winning the New York lottery, hitting 4 consecutive numbers, if there are, 6 consecutive numbers and there are 54 numbers altogether, I don't know if that's still the way they play the lottery, it would be 54C6, because that is the possibility of getting a combination of any particular combination of 6 in a row when you have 54 possibilities. The way you figure this out, by the way, and it's not going to be so relevant for this particular question, but the way you'd figure out 54C6 is take 54 factorial 6 times. In other words, 54 times 53 times 52 times 51 times 50 times 49. I think I'm running out of space over here. You probably can't see the 49 over here on the left side, but you can imagine that it's there, and put it divided by 6 times 5 times 4 times 3 times 2, and then times 1, which is the same thing. You can multiply this out, and you can figure out that the odds of winning the New York lottery are 1 in a lot. I don't know. Whatever the case may be, hundreds of millions of possibility, or 25, I don't know. It's many, many millions of possibilities. But what you need to do for this sort of thing is you need to figure out 10C to the number of possibilities you have, the number of different combinations you have. Now, in this case, for the 0, there is no combination. It's just 10 of not married. So you'd put 26C0. I'm sorry, 10C0. For the 1, it would be 10C1. And for the 2, it would be 10C2. But that's not the end of it, because for each one, you also have to put in the odds of each particular one occurring. So, for example, you would need to put, for the first one, there are 10 that are married and none that are never married. So it would be the odds of each one individually, which is 0.6 times 0.6 times 0.6 times 0.6 10 times. In other words, if you grabbed any particular 10 women, you'd have to get a non-married, 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 non-married 10 times. So you'd have to put that to the 10th power. For this one down here, you would have a married, which we'll call 0.4, and then 9 non-marrieds. So we'll multiply that by 0.6 to the 9th power. For the third possibility, where you have two that are non-married, you'd have 2 non-married, so 0.4 times 0.4, which is 0.4 to the 2nd power, times 0.6 to the 8th power. So you got to multiply the various chances here. So for the first one, let's use a calculator. I'll put this calculator up here. Okay, all right. Now, for the first one, we're going to use 10C0 is nothing. We're just going to leave that. You don't have to do any functions because you're not multiplying anything. So we'll do 0.6 to the 10th power. For that, we can just do 0.6. We'll use the power function, which is shift and y to the x. You don't have to know how to use this kind of calculator, but I'm doing that to the 10th power. And that gets you 0.604. So I'll write that 0.604. What did we have? 0.046. All right, we'll leave it to 4 places. That should be fine. The second one we have. Now the second one, so we'll clear it. The second one was 0.4 times 0.6 to the 9 power, so we'll do 0.6 to the 9th power. How do we do that? We'll do the y to the x function to the 9th power, which is that number. Then we have to do it times 0.4, so we'll do times 0.4 equals that. And then we have to multiply by 10, because 10C1 is 10. 10C1 is 10, and it's only 1, so you just divided by 1. So, just like 10C5 would be 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2 times 1. So 10C1 is simply 10 times 1, which is 10. So multiply that by 10, which only means we have to put one more. We just have to move the decimal point over one spot, what is it, 0.0, instead of well, we can just multiply it by 10 over here on the calculator, get 0.403. So we'll say 0.0403, okay. Now let's try the last one. And the last one is 10C2. Now, first of all, 10C2 is how much? 10C2 is 10 times 9 over 2 times 1. So 10 times 9 is 90. Divided by 1 divided by 2 is 45. So we'll put a 45 over here. Then we will do, let's say, 0.6 to the 8th power. So 0.6 to the 8th power is this. Now 0.4 to the 2nd power, 0.4 times 0.4 is 0.16. So multiply that by 0.16. Okay. And then we have to multiply that by the 45. So multiply that by the 45, and we get 0.1209. Okay, 0.1209. And if we add them all together, all right, just add this to the 0.0403, and add that to the 0.6046, and our total answer. I'm sorry, this up here I made a mistake when I transcribed it. This was 0.006406. Sorry about that. So let's add it up on the calculator again. Okay, so we had 0.006046 plus 0.0403 plus 0.1209, and altogether we had 0.1672. We'll round it off for 0.1672. In other words, based on these circumstances, the odds of getting 0, again, the odds of never married are 0.4, odds of once married are 0.6, so the odds of 0 married are very, very low, 0.006046. It's less than 1%, about 0.6%. Then we had the odds of having 1 married were 0.0403, about 4%. The odds of having exactly 2 married were about 12%. So the total for these three were about 0.1672, or approximately 16%. Okay, next. Now we're going to get a little bit easier, thankfully. All right, basketball player Chauncey Billups of the Detroit Pistons, I don't think he's playing anymore, but anyway, it makes no difference, makes free throws at 88% of the time. Pretty good free throw shooter. Find the probability that he misses his first and makes the second. So we need and possibilities here. So the first one was the miss. What are the chances of a miss? 12%, because if 88% is a make, so 12% is a miss, so we'll put 0.12. The second, we had the possibility of 88% of a hit, so we'll do that. So since we want the two possibilities multiplied by each other, which is 0.2. Let me clear that. 0.12 times 0.88, and it looks like our answer is what, about little over 10%, 0.1056. Okay, 0.1056, which is about 10.56%. So those are the odds. Again, just multiplying since they're and. If it was an or, you would add these two chances, which would be, well, if it was a make or a miss, obviously it would be 100% because those are the only two possibilities. And 0.12 plus 0.88 is 100%. But 0.1056 or 10.56% is your answer there. Number 22 is find the area of the shaded region under the normal curve. So we're going to use the z-curve, the z-table, and that is over here in the materials. This is the normal distribution table, and you'll get a copy of this on the exam. This is a very easy question. They want to know the region under the standard normal curve. So remember, this chart, the way this works is something like this is 0.00, 0.01, 0.02, 0.03, then 0.11, 0.12, 0.13, etc. So what do they want? What do we want over here? We want the whole region of the area under the standard normal curve all the way to 1.3. So 1.30 is right here. 1.30, that's this chart over here, 0.9032 it looks like, just based on this chart. That's the area of the larger population. But what this wants to know in English is it wants to know the odds. This is the middle, the mean of any particular distribution, of a normal distribution, and this is this direction. This is 1.3 standard deviations to the left. In other words, they want to know what are the odds that whatever or what's the distribution? If you take the total number of results in this particular statistic, if you take all the results higher than the mean and all the results lower than the mean up to 1.3 standard deviations, what percentage? What's the total percentage of the curve? And according to our distribution table, it should be 0.9032, which is 90.32%. So that's our answer, 0.9032. Okay, next one is also relatively easy. Find the area of the standard normal curve to the left of z equals 1.25. The z is they don't draw you a chart over here, but it's the same basic question. They want everything to the left of the positive 1.25, which means everything left is lower and the right is higher. So they want everything less than the mean, and everything higher than the mean up to 1.25 standard deviations above the mean. Okay, how do we figure that out? No problem. Use the same chart. It says a normal curve. That's the z table. Z table is normal distribution. So let's just find 1.25. Here's 1.2, and slide over to the 5, and it looks like we've got 0.8944, which is 89.44%. Same basic question as we had a moment ago. They didn't draw you a chart, but it makes no difference. If they wanted to the right, by the way, let's say they wanted to the right of 1.25. Well, to the right of 1.25 is 1 minus 0.8944, which is a little over 10%, about 10.56%. The reason is to the right, they want everything above 1.25 standard deviations above the mean. Here they want everything to the left, where they want everything below 1.25 standard deviations above the mean. In 22, for example, let's say they wanted something, let's say they wanted the area of the non-shaded region. So they wanted this area here. Well, then you would take the area of 1 minus whatever this is. Now, this happened to have been 9.9032, so the area to the left of it, this non-shaded area, would have been 9.0968, 9.68%. Obviously a much smaller number. Okay, next question. IQ tests are normally distributed within a mean of 100 and a standard deviation of 15. Individual's IQ score is found to be 90. Find the z-score corresponding to this value. Now here, actually, they give you, you don't have to use any tables or anything like that. All you need to do is really find just the definition of the z-score. Now, what the z-score means is the difference from the mean divided by the standard deviation. That's the general formula. Let me write that down for you over here. Here it is. The z-score is the difference from the mean divided by the standard deviation, or the sigma. Sometimes you'll have to find the z-score using the chart if you're not given the difference from the mean and the standard deviation. But over here they actually give it to you. So the difference from the mean in this case is simply 10, 100 minus 90, or 90 minus 100 makes no difference. You have to use the absolute value either way. And then you divide that by the standard deviation of 15. So it's 10 divided by 15, which is 0.66 or 0.67, something like that. It's actually negative. The individual IQ is found to be 90, so it's actually negative. The distance from the mean is negative 10. So it's actually you can call it 0.66666666 away from the mean, or you can call it negative 0.666666 to illustrate that it's lower than the mean. Number 25. Find the z-scores for which 90% of the distribution's area lies between z and negative z. Now, of course, once again, we are going to look at the z-table, the normal distribution table, which I'm going to shift over for you right here. Okay, now here we're talking about, again, the question was 90% of the distribution is between z and negative z, which means that overall, that's kind of a question that's a two-tailed question. We're talking about where 90% between z and negative z, which means you have 5% extra on each side, because that would leave the 90% in the middle. That's kind of the question that you're asking. This is the one-tailed distribution chart. For a two-tailed distribution, you just have to figure out, okay, they're asking for 90% of the distributions between each side, so where does each one have to be? Now, in order for 90% to be in the middle, the two boundaries have to be at 95 and 5. That, of course, is the only possibility to have I mean, picture this one that we saw before from the previous question. Now imagine if there was a white space over here and a white space over here. So in order for that to happen, you'd have to make sure that each one, it's on the 95 and the 5 in order to have 90 in the middle. So we want to figure out what's the 95 percentile, where you would have one border of the normal table. And for that, we would simply look through the page until we find about 95%. And it looks like I'm just right over here is the first one with 95%. Here's 94.8, 94.9, 95%. So we'll look at this one. This one is the 1/6 row and the 0.05 column, so it's about 1.65 either way. In other words, positive 1.65, which would be 95%, or negative 1.65 away from the standard deviation, which would be at the minimum, which would be at the 5%. That's how you would get 90 in the middle, by putting the 95 on one side and the 90 on the other side. So I guess the answer would be plus or minus 1.6, approximately 1.65%, or 1.65%, approximately 1.64%, 1.65%, somewhere in between those two. So that's how you would write it, plus or minus either positive or negative 1.65%, approximately. Number 26. Use the central limit theorem, which is basically the same thing as we've been discussing all course, the standard deviation rules we've been discussing all course, to find the mean and standard error of the mean in the sampling distribution. Well, the amount of time it takes employees of a telecommunications company have worked for distributed with a mean of 5.1 years and a standard deviation of 2.0. So first of all, we know right away what the mean is. It tells you what the mean is. The mean is 5.1 years. The standard deviation is 2. Random sample size 18 are drawn from the population. So when you're talking about the standard deviation of a particular mean, you may recall from this slide from the materials, you have to divide the standard deviation by the square root of the sample size. That's the first step of finding the standard deviation of a particular population mean. Like we have over here, we're given a number of 18, and we have to divide the sample standard deviation by the square root of the sample size. So in this problem, the sample size is 18, the square root of the sample size, and we figured that out using a standard calculator. Let's bring up a calculator over here. We will take 18 and use the square root function, which is over here. It tells you 4.24, approximately 4.24. So we'll take the regular standard deviation, which was 2.0, and we will divide by 4.24. And let's get our calculator back up. So we have 2 divided by 4.24, and we get an answer of 0.47. So our standard deviation of this particular population mean would be 0.47 is what we're looking for over here. The standard deviation overall, of course, was 2, but when you apply it to a particular population mean, you just divide by the square root of the sample size. Okay, find the critical value 27 of the ZC, which means the z-table result, of that corresponds to a 95% confidence level. Now remember, a confidence level means in either direction. So that is a two-tailed distribution. Not a one-tailed distribution is if you were looking for everything below a certain point. Here you're looking for a confidence interval, which means you want it to be that far away from the median, from the mean. And so 95% confidence level means it has to be overall on the scale of 0 to 100, it has to encompass 95 points. So it has to start at it has to start at 2.5% and end at 97.5%, kind of similar to the one that we did before, number 25. So how would we do this? We want a 95% confidence interval, so let's look at the z-table. And we want since this is a one-tailed, remember, this, as you can see from the diagram over here, this is based on a one-tailed distribution. So for a two-tailed distribution, we have to look at what's going to be all the way up to 97.5. So if we scroll around, we got to look for 97.5, which looks like it's right around over here, 0.9750. And that goes at 1.9 row and the 0.06 column, so that's 1.96. So it can be positive 1.96 or it could be negative 0.196. In other words, it has to be either 1.96 up to 1.96 standard deviations above the mean or up to 1.96 standard deviations below the mean. Just the important thing here, as with question 25, is you have to remember that you're talking about a two-tailed distribution when you're looking at confidence interval, and so you have to adjust for that as when you're looking at the z-table, which is based on a one-tailed distribution. Number 28 is a little bit more complicated. Number 28 asks you to build a confidence interval. And if you don't remember, there was a tutorial in the crash course. This is slide 26 that tells you how to do the confidence interval. I did a couple of examples in the crash course, but now we're going to look at an example from right over here. And the example is a random sample of 40 students, a test score with x, which is the mean of 81.5, and standard deviation is 10.2. Construct the confidence interval for the population mean, which means the mean of these 40 students, if c, meaning the confidence interval, is 90%, or 0.9. I'll write the key numbers over here. And we've got the sample size of, let me make this a little thinner. Okay, the sample size is 40. We've got a mean of 81.5. We've got a standard deviation of 10.2. And we've got a confidence interval of 0.9, or 90%. Okay, so how do we do this? The first thing we got to do is figure out our population mean. And the population mean is the overall standard deviation divided by the square root of the mean, of the square root of the sample size. So how do we do that? What's the standard deviation? Standard deviation is 10.2 divided by the square root of 40. And we can do that on our calculator over here. Let's drag our calculator here. Let's take the square root of 40. And we'll use two places. Okay, 6.32. So we'll say 10.2 divided by 6.32, and it gets us 1.61. So our population standard deviation is 1.61. Now we want a confidence interval of 90, and remember, confidence intervals are two-tailed distributions, as we've seen already. So we're going to find the z-table, which is up here. Okay, and so with a 90% confidence interval, you need a 95 to 5. So you need to use the 95 value, which is 1.65 if I recall correctly. We'll round it off to 1.65. It's right about 95%. Again, we'll round it off. It's close enough. Okay, so it's 1.65 standard deviations. So in order to get the 90%, generally, in order to get the 90% confidence interval, you need to get it within 1.65 standard deviations. So it's 1.61 times 1.65. In other words, 1.65 standard deviations, and our population standard deviation is 1.61. So let's do that in our calculator. We have the 1.61. We'll multiply by 1.65, and we get approximately 2.66. So it looks like we have approximately 2.66. And if you round it off, you might get a number that's a little bit higher, a little bit lower, but you should get something to that effect. Okay, number 29. Find the critical value TC. This is the first time we're going to use the t-distribution table. Until now we've used the normal distribution table. Remember, the t-distribution table is for smaller sample sizes, for a confidence interval of 0.99 and a number of 10. Now, if we go to the t-distribution table, if you recall, first of all, we can use the two-sided, unless stated otherwise. A confidence interval, again, as we discussed the last few questions, generally means two-sided, either direction. If it's only one direction, you would use the one-sided, but a confidence interval typically requires you to look at the confidence that you're looking at in both directions. And for the number, this is the degrees of freedom, and that's the number of sample size minus 1. First one is always established, so the degrees of freedom is always n minus 1. So in this case, this is question number 29, we had n equals 10, so the degrees of freedom is 9. And the C, the confidence interval, is 99. Let's see. So we'll take the 9, and we'll go across until we hit the 99 column on the two-sided data, which is over here. And it looks like your answer here is 3.250. Simple enough. Okay. Number 30. When 435 college students were surveyed, 120 said they owned their own car. Find a point estimate for the population proportion of students who find their own car. Well, that's a really complicated way of saying the average. Remember, they're not asking for a standard deviation. They're not asking for anything complicated over here. They're just looking for a point estimate. A point if you just start off with the mean, start off with the average. So 435 and 120 have their own car. So that would mean that 120 divided by 435, which is what? Well, let's take out the calculator. Simple enough. 435 divided by 120 is your mean. I'm sorry, of course it's the opposite. If you want the percentage of students, so you need the 120 divided by the 435. Obviously you can't get a number above 1 when you're talking about a percentage. So let's do 120 divided by 435, and what do you get? Looks like you get approximately 0.28. Or if you wanted to display it a little further out, it would be 0.275. You could round off to 0.276, or you could round off to 0.28. Any of those would be fine. Okay, 31. Construct a 95% confidence interval. Again, this one's going to be a little more complex, kind of like question number 28. 95% confidence interval for the population standard deviation. That's the alpha of a random sample of 15 men who have a mean weight of 165.2 pounds and a standard deviation of 13.5 pounds. Assume that the population is normally distributed, which means we're going to use the z-table. Even though normally when you have 15, you'd use the t-table. Here the question specifically tells you to assume a normal distribution, so we are going to use the z-table. So let's go ahead and do that. Let's go back to our board over here, and we will write the key numbers. That's always what you want to do, obviously. All right. So what do we got here? It looks like we have our confidence interval is 95%. Okay, we've got a sample, a number of 15. We've got a mean of 165.2. We've got a standard deviation of 13.5. Okay, so the first thing we want to do is we want to get the population standard deviation. The population standard deviation, remember, is the general standard deviation divided by the square root of the sample size. So that means, in this case, 13.5 divided by the square root of 15. Okay, let's get out our calculator again. Clear it. And what do we got here? We got, let's take 15 and take the standard deviation of that. Take the square root of that, which is 3.87298. So we will take 13.5 and we will divide it by what did we have over here? 3.872. We can round it off to that. And so we've got a population standard deviation of 3.487. We'll call it 3.487. That should be plenty of digits. Okay. So now, what is our confidence interval? In other words, how many standard deviations apart do we want? Well, let's take a look at the z-table. Here's the z-table. And we want a 95% confidence interval. Again, then we've we've got to use the 97.5 because it's two-tailed, like we discussed before many times. And that, I think we've seen already, is 1.96, I believe. Yeah, right there, 1.96. So we're going to do 1.96 standard deviations in order to establish the confidence interval. So 1.96 standard deviations times, and each standard deviation is 3.487. So let's do the 3.487. Get the calculator back up here. 3.487 times 1.96 standard deviations, and we get approximately 6.83. And if we want to round it off a little bit, we'd get, let's call it 6.835. Is 1.96 standard deviations away from the mean. So we could have 6.8, we'll round it up to 6.84 above and 6.84 below. So the 95% confidence interval, assuming the mean was 165.2, we'll add 6.83, 6.84, excuse me, and you get 172.04, and then you subtract 6.835, and you get 158.37, or 158.38, excuse me, approximately. Anyway, so this would be the confidence interval. Your confidence would be 95% that any given one would be between these two numbers. Question number 32. A brewery claims that the mean amount of beer in their bottles is at least 12 ounces. Determine whether the hypothesis test for this claim is left-tailed, right-tailed, or two-tailed. Well, if you recall from the crash course, the tailed hypothesis test looked as follows. It depends which side of the distribution, this is a normal distribution, where you have the low end over here, the high end over here, and the majority of cases in the middle over here at the highest point. This is a normal distribution. And a tailed hypothesis test is a hypothesis test that looks to see whether something is greater than a particular number, less than a particular number, or in between two extremes. A left-tailed number is one that tries to test the lower end of the range, to try to make sure that something is or is not at the lower end of the range. A right-tailed hypothesis test is to try to make sure that something is or is not at the upper end of the range, and a test that tries to make sure that something is in the middle, in between two extremes, is a two-tailed test. So our example over here, here's a couple of examples you may recall. If you're testing the left side, the greater than, then it's right-tailed, which means if your null hypothesis claims that the effect is no greater than x, well then you have to try to see if you can find any results that are greater than x. Because if you do find results that are greater than x, that's not a good thing. If you're testing less than, on the other hand, then it's a left-tailed test. So if I say, for example, I am claiming that it will rain no more than 100 days this year, well, that's a right-tailed test, because we're looking at to see if there's anything more than 100. We're trying to test that orange area over here. Whereas if I'm trying to say that there will be no less than 100 rainy days a year, that's a left-tailed test, because we're looking at the lower range. We're looking to see, in order to prove or disprove the statements, we're going to look to see if there are too many bad results in the lower end of the spectrum. Or you can just remember that if you're testing less than, then it's left-tailed. If you're testing greater than, then it's right-tailed. So in our case, question number 32, a brewery claims the mean is at least 12 ounces. So that would be an example of a left-tailed test. Why? Because you're trying to see, are there results that are below 12 ounces? That's what we're looking for. If I make a claim, it doesn't matter how high it is. It could be 15, 16, 100, 150. That makes no difference. But we're trying to look to see, are there any results below 12 that are going to be problems? And if there is, so because we're looking at that lower end of the spectrum, we're looking at that left side to see if there are any danger areas in there, then we're going to look at a left-tailed test. Question number 34 is very similar. Question number 33. The owner of a professional basketball team claims that the mean attendance at games is over 30,000, and therefore the team needs a new arena. Well, that seems to be the same kind of question. The word over means we're testing for at least. Really, it's really the same claim. The brewery claims that the bottles have at least 12 ounces, and the basketball team claims that the stadium has at least 30,000 people. And this would also be a left-tailed test. So for the same reason, they are both left-tailed tests. Okay, number 34 and 35, I actually have the answers written over here. And I'll tell you why they are in a minute. First, let's go back and look at the null and alternative hypotheses. And we covered that in the crash course as well. A null hypothesis, or H0, is the assumed position, or the default position. If I make a claim, then that claim is the null hypothesis. If I claim the mean exam average is 75, mu, this over here, which is the median, it's a Greek letter that means the median in statistics, is 75. So my claim that the average is 75 is the null hypothesis. The alternative hypothesis would be that it's not 75. And so how would we phrase that over here? Well, 34 says the mean age bus drivers in Chicago is 59.3, which means our null hypothesis is this. In statistics, that's what our null hypothesis is. The average is 59.3. That's really what it's all it means. If a hypothesis test is performed, how would I interpret a decision that fails to reject the null hypothesis? Well, I would say something like this. There's not enough evidence to reject the claim that mu is 59.3. Same basic idea. 35 is the converse. The mean IQ in statistics teachers is greater than 160, which I don't think it is, but anyway. So if a hypothesis test is performed, how should you interpret the null hypothesis? Actually, there's a little bit of a mistake here. What is the null hypothesis? The null hypothesis is that the IQ is greater than 160. So that's the null hypothesis. Mu is greater than 160. In mathematical terms, that's how we would write this. If a hypothesis test is performed, how would you interpret a decision that rejects the null hypothesis? You would say something like this. I'm sorry, over here, how would you interpret a decision that rejects the null hypothesis? Then I would say there is enough evidence to reject the claim that mu is greater than 160. Same basic idea, except 34 was saying there's not enough evidence to reject the claim. 35 is saying that there is enough evidence to reject the claim. Okay, 36. Let's see. We've got find the critical value for a right-tailed test. There was a one-tailed. With an alpha of, in other words, a confidence interval of probability of 0.01, that's 1%, and an n of 75. Since the number is more than 75, we're going to use the z-table, the normal distribution table. Remember, if it was less than 30, we would use the t-distribution table. We'd use the t-table, but we're going to use the z-table here. So we want 1%. And remember, before, when we were looking at confidence intervals in the middle, we had to take half of this, whatever number was in here, because this is based on a one-tailed distribution. Well, fortunately, our question over here specifically asks for a one-tailed distribution, a right-tailed distribution. So we want 1%. So let's look for the 99% a level of certainty, and I'm looking down here looking for the 99, and it looks like the 99 is somewhere right around here, 99.0. It looks like this one is right around 99%, 99.01%. So, what is the number of standard deviations away from the mean that you need on a one-tailed test for 99%? Let's look at the columns. It's 2.3 and and this is the O3 column, 2.3 row. So for 99% for a one-tailed distribution, you'd need about 2.33 standard deviations, it looks like. Okay, so that's fairly simple. Question 37, a little bit harder. Standardized test statistic t for a sample with n equals 15, the number equals 15. Now this is going to be so you know that we're right away going to use the t distribution chart and not the z distribution, not the normal table. X, which is the sample, the mean of the sample, excuse me, is 7.4. The standard deviation is 0.8, and the alpha is 0.05. In other words, a 5% confidence interval. Okay, and our null statistic is mu, or the mean, is less than or equal to 7.1. So if it's less than or equal to 7.1, remember, less than or equal to, do we want a one-sided distribution or a two-sided? Do we want a one-tailed distribution or two? And the answer, of course, you can pause it and think about it for a second. The answer, of course, is that we want a one-tailed distribution, because if we're looking at how far something is away from the mean, then we're worried about it being too high or being too low. Over here, we said that the mu is under 7.1, so the only thing we're worried about is it being too high. So it's a one-tailed distribution. So it's a one-tailed distribution, that's no problem. So we have to find an alpha of 95% for a one-tailed distribution. Now notice we're talking about an n of 15, a sample size of 15. So on the t-distribution chart, you always take the degrees of freedom, which is n minus 1. So we're going to look on the 14 line under a two-sided distribution, a one-sided distribution with a 95% alpha, 95% confidence interval. So let's go down this column, and we're going to look at the 14, and that looks like we've got 1.761 as far as I can tell. So we've got that number of standard deviations. So we're talking about 1.761 standard deviations. I'll write that down over here. 1.761 standard deviations away from the mean. Now, and once we have 1.761 standard deviations, so it would be multiplied by the number of the actual standard deviation, which we said before was 0.8. So for example, if we multiplied this by 0.8, we would get this number of standard deviations. I'm just going to multiply it out. Where's a little calculator here? And we've got 1.761 times 0.8. This would be the number of standard deviations away from the mean, approximately 1.41. I think if I did it on my calculator, it comes out to about 1.402 if you round it out to 2 more decimal spots, but it's approximately that. So it's 1.402 away from the mean, and since our null hypothesis was that the mean is less than 7.1, we would have to make sure that whatever our statistic is, whatever mean we get in terms of the sample, that we're sampling with these 15 people, would have to be less than 1.402 away from that number. Next question is question number 38, and we're asked to construct a 99% confidence interval for dataset A. In other words, based on these 10 results, how confident can we be that the real mean, that the real average of any particular population with these results are within a particular framework? Now, the way to do this, the way to get it would really be kind of cumbersome to do it by hand, and the first thing you need to do is you need to figure out the average. Now, to figure out the average, you can add them all up and divide by the divide by the total number of sample sizes. Now, you could do this by hand, you could do it by calculator. For the sake of speed, I'm going to do it with Excel. Again, you're not going to have Excel on the exam necessarily, but it doesn't really pay pedagogically to show you how to do it because it's fairly obvious. You have a calculator, you type them all into the calculator, and then you press divided by the total number of sample sizes, which is 10. So instead, I'm just going to use the Excel's average function, which is the average of all of these, which will tell us very simply. Okay, that's 7.03. That's our average. Now, in order to figure out the standard deviation, now if you recall, the standard deviation formula was to square each value's difference from the mean, and then add them all together, and divide them by the sample size, minus 1, and then take the square root of the result. Also a fairly cumbersome process. So for example, to take these values that we have over here, if we wanted to do it one step at a time. Now Excel actually has a standard deviation formula, which you can just plug in right away without having to figure it out at all. But let's just, just for kicks, we'll do it the slow way, just to kind of illustrate each's point. So for each one, I'm going to take 7.03, which was the mean, minus whatever is in this box. So the difference between each of these and the mean are these columns. 1.23. This one is 0.23 below the mean. This is 1.23 below the mean, and these are all actually above the mean. Actually, the way I really should have done it, I'm going to change it. I'm going to take for each one. I'm going to take really 7.03. minus whatever is in this box. That's actually probably a more correct way of doing it. I'm sorry, the opposite. I'm going to take this, whatever's in this box, minus 7.03. Either one is fine. I mean, it wouldn't matter in terms of the result, but I'm going to do it this way. I think that's a little bit more intuitive in terms of how it comes out. So over here we've got it's 1.23 below the mean, all the way to 8.3, which is 1.27 above the mean. Then we take the squares of all numbers. Let's go back to the standard deviation formula, and the next step in calculating standard deviation is square all of the values' differences from the mean, and then add them together. So I'm going to square each value, and in Excel, again, this is not really necessarily a lesson in Excel, but certainly Excel helps you with these things. You can do this on a calculator too, just multiply it by itself. So for each one, we are going to raise it to the second power. In Excel, to raise it, you just use the little caret over there, and I'll copy the formula down. So these are all these numbers squared are these numbers. Then you need the sum, or the total amount of all these combined. You got to add all of these together. Remember, the formula was to square each value. Let me bring that over here. Square each value's difference from the mean and add them all together, and then divide the number by the sample size and take the square root of that result, of that number. So let's add them all together, and you could do it on a calculator, or in Excel you can just do a sum function equals the sum of all these, and you've got this amount, and then you can divide that by the sample size minus 1. You can do that on a calculator too. The sample size over here is 10, so it would be this, so that n minus 1 would be 9, so it would be this divided by 9, and then you would have to take the square root of this number, whatever that happens to be, equals square root of this particular number, which is 1. Okay, so this is our standard deviation. Now, if we wanted to do it a little bit more efficiently, if we were using Excel, I mean, that's the mechanics. The mechanics of it is you take each result's difference from the mean, square it, add the results, divide by the sample size minus 1, take the square root of the result. If we were actually using Excel, we could save a lot of time and a lot of hassle by using the standard deviation function. You can just see equals stdev, which is standard deviation, and take all the original results And Excel does the whole process for you. Notice it's the same as we got over here, thankfully. It better be the same, or else it means we would have done it wrong. But Excel is nice enough to do that for you. So either way, we've got the standard deviation. So once we've got the standard deviation, now we have to figure out the confidence interval. And the first stage in figuring out the confidence interval is looking at the z-table. Now, where's the z-table? The z-table is over here. And here we're asked for 99%. Now remember, as we discussed earlier, this is a one-tailed distribution table. A confidence interval, on the other hand, means in either direction. So it's a two-tailed. So instead of 99%, we're going to have to look for 99.5%. So we're going to look for the value of 99.5, which looks to be approximately this one, which comes out to about 2.58, we'll call it. It's right in between 2.57 and 2.58. We'll round it off to 2.58. And so we'll say we need a confidence interval of, so we have to multiply this number, which we can do in a calculator again, or you can just in Excel, you can multiply it by 2.58, and so our confidence interval is approximately 2.805, or closer to approximately 2.81. We'll round it off to, since actually it's asking us to round. It actually asks us to round it to the nearest tenth. So the nearest tenth would be 2.80. Or you can actually, it's more correct to just write 2.8.